Okay, so let's go ahead and do a few more examples of 11.9. The section I think is called Representations of Functions as Power Series. But basically it has to do with manipulating power series by simple operations up to and including differentiation and integration, because they're polynomials or infinite polynomials with infinite number of terms, they do actually behave when you take the derivative just like a polynomial does, and you can differentiate term by term or integrate term by term, and when you do that, that does not necessarily it doesn't mess up the fact that there's a pattern. The pattern persists, it just becomes a different pattern. And we saw that in a couple of the examples that we did in the last one. Now let's go ahead and to start off this second video, let's go ahead and just start off with a relatively easy one. Okay. Now, we recognize the fact that 1 over 1 minus x is 1 plus x squared plus x cubed plus dot 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 dot. And that is sigma as n is equal to 0 to infinity of x to the n. Okay? Now, what do I need to do here? Well, in order to transform this into this, it winds up being relatively simple. I simply need to, instead of putting x there, I need to put x cubed. So it's 1 plus x cubed plus x to the 6th plus x to the 9th plus dot 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 dot. And that is no longer n is equal to 0 to infinity of x to the n, but x to the 3n. And then in order to get the coefficient on top, I simply have to multiply through by 3, which really isn't that big of a deal. Becomes 3 plus x cubed, or 3x cubed, plus 3x to the 6th, plus 3x to the 9th. And then I can either put the 3 out in front, or I can include it within the body of the sigma notation. Let's go ahead and include it in the body. And I wind up with that. That is the sigma notation representing this function f of x in terms of a power series. Now, one that's a little bit more difficult, and we're gonna do a couple here that that cause us to scratch our head and say, this one is a bit like one that we've already done. This is x over 1 plus x squared. Okay. Now remember, what happened in the last video, and let's see if I can bring this back. We went through this process, right? We started with 1 plus x, and then we went to its derivative, multiply through by a negative, and then multiply through by 2. We're going to do something similar here, except for instead of multiplying through by 2, we're going to multiply through by x. Okay. So we have 1 over 1 minus x, and you might as well just go ahead and start at the beginning. N is equal to 0 to infinity of x to the n. And of course, when I change it into 1 plus x, I turn that into an alternating series, and I'm left with negative 1 to the n times x to the n. Okay? Now, I need to go ahead and take the derivative of this, and it winds up being negative 1 over 1 plus x squared. And when I do that, just like I said in the last video, it doesn't change the alternating nature of this, but I do get n times x to the n minus 1. I simply use the power rule. Well, I want to get rid of that negative because my function that I'm trying to get at doesn't have a negative. It's just got x in the numerator. So let's go ahead and get rid of that. Like I said in the last one, that doesn't do anything but change which terms have a negative and which ones have a positive. So instead of negative 1 to the n, it becomes negative 1 to the n plus 1. So instead of the second, fourth, sixth, and so on terms being negative, I have the first, third, fifth terms being negative. And then I simply need to multiply through by x. And when I do that, that winds up giving me negative 1 to the n plus 1 times n times x to the n. Okay, all I've done is just basically multiply this by n, taking away that negative 1 right there and leaving it just as x to the n. This is the manipulation of the power series. This is the power series for this function, and all we did was we started at what we knew and just did simple operations. Substituted in negative x for x, took the derivative, multiply through by a negative, multiply through by x, and each step really wasn't all that difficult, but each step was actually necessary in order to transform the power series, the function representative as power series that we knew, into one that we were looking for. Okay? Well, let's go ahead and continue along sort of this trajectory. I got a couple more picked out for us to do. How about f of x is equal to natural log of 1 minus x? Well, I tell you what, let's put that one on hold for a second. Let's actually do 1 plus x. Well, we happen to know that 1 over 1 minus x, as we've seen so many times, is x to the n. And of course, 1 over 1 plus x is n is equal to 0 to infinity of negative 1 to the n times x to the n. How do I get from 1 over 1 plus x to natural log x? And you're right, you'd anti-differentiate or integrate. So we have natural log of 1 plus x is equal to, well, that doesn't change the alternating aspect of it any more than differentiating does. And I just do the undoing of the power rule, and that right there should be it. So if I've done that one, then doing, say, g of x is equal to the natural log of 1 minus x shouldn't really be that much different, right? But instead of going to this step right here, we're going to, n is equal to 0 to infinity of x to the n. We're going to go ahead and we have to have a negative in that numerator to ensure that the numerator is the derivative of the denominator in order to properly integrate. So we have negative 1 times x to the n, and then when we take the 1 minus x is equal to sigma, n is equal to 0 to infinity of negative 1 x to the n plus 1 over n plus 1. And that winds up being our power series based upon differentiation. Now, obviously you can continue going along this route and starting off with sort of our magical power series and moving on. And we're going to do a couple more like that. But this principle holds for any power series that you know in order to actually arrive at a power series that you're looking for. It doesn't have to necessarily start with what we're doing here. It doesn't necessarily have to be one that can be arrived at through using 1 over 1 minus x is equal to sigma, n is equal to 0 to infinity, because we are going to be learning a couple more power series that you're going to wind up memorizing, and you can use those. But, while we're doing these, let's go ahead and I just wanted to at least make a nod to the fact that, that it isn't exclusively starting here. You can start with whatever you need to start with as long as it is a known power series and you are simply applying simple operations up to and including differentiation and integration to that known power series. You can start off with whatever power series you want and manipulate whatever power series you want in order to get at what you need. Okay, well, let's say I'm looking for arctan of x. Well, I know that I can actually, I know that this is the integral of that, okay? So what I need to do is I need to transform this original power series into that in order to integrate. So let's go ahead and let's do one that we already know, and we know that it's negative 1 to the n times x to the n. And then if I want to transform it into x squared, that winds up being n is equal to 0 to infinity of negative 1 to the n of x to the 2n. Now, if I'm going to integrate this, I need to add 1 to that, right? And it winds up being arctan of x. And, like I said before, the differentiation and integration doesn't change the alternating aspect of it, but I need to add 1 to the exponent and divide by the new exponent. And that should be our power series. Okay? So let's say we're actually asked instead for not arctan of x, but arctan of x over 2. Well, now that this one is known, I simply have to manipulate this one. Okay? And if I just want to manipulate that one, it becomes arctan of x over 2 is equal to sigma, n is equal to 0 to infinity, of negative 1 to the n, x over 2 to the 2n plus 1, all of that over 2n plus 1. And all I've done is just basically taken what was x and plugged in x over 2. That right there is the power series, that's the sigma notation of the power series that I'm looking for. And so, as long as we're just very methodical in moving forward and starting from one that we know and doing just very, very simple movements in each particular step, you don't get overwhelmed with how the sigma notation is transforming in each step. My advice would be to just start with one that you know and just do one thing at a time and manipulate it until such time as you arrive at what you're being asked for. Okay? And that's basically the long and short of manipulating power series, either by multiplying through by something, by plugging in something, an expression of x instead of x, by integration, by differentiation. You simply need to remember what I said by the fact that when you manipulate the power series by differentiation and integration, the radius of convergence remains the same, but you need to recheck the endpoints to determine whether the interval has changed, whether one of the endpoints, whether the inclusivity of the endpoints has changed from non-inclusive to inclusive, meaning that a parenthesis to a bracket or vice versa, and that can happen just based upon the nature of the functions that and how they're and their domains and everything like that. That kind of brings us to the end of 11.9. 11.10 is where we start constructing power series. And that's why it's called Taylor and Maclaurin. Taylor and Maclaurin were mathematicians who basically formalized the methods by which we construct these. And that winds up being a whole lot of fun, and we'll get on to that in the next video. So any questions, please do email me. Otherwise, I will just look forward to hearing from you when I see you next. Bye.